with a jump back a bit to the beginning of today's meeting with some more work on test cases. So pleasure to welcome James Kent, who's going to tell us about tracer transport tests in DCMIP.
Thanks, Nigel. Yeah, so I'm going to be talking about the tracer transport tests that took place at DCMIP. So DCMIP is the Dynamical Core Model and Comparison Project. So this was a workshop that took place over 2 weeks in July and August earlier this year. The aim of the workshop was to bring together lots of different modelling groups to highlight the newest modelling techniques and present a standard set of test cases to assess these models and these techniques. So for more information, see Christiana's talk, which isn't on Friday, it's actually later today. So 18 models took part, and we also had 40 students working with the models. And the point of my talk is to focus on the tracer transport tests and present a few select results from the workshop. So as we heard in a couple of sessions earlier in the week, tracer transport is very important. If you're moving hundreds of gases around the atmosphere, it's very important, especially in climate prediction studies. The test cases we use have an analytical solution. So what this is, it's because we either reverse the flow or advect once around the globe. We can use the initial conditions as the analytical solution. And this gives us a chance to calculate error norms and assess where our models are doing well and when they're doing badly. So the tests that we created for DCMIP, they're really designed to investigate the things that are important for tracer transport. So that's things such as monotonicity and positivity. So if your tracer scheme's giving you negative values, not only is that not physical, it's likely to crash your physics routines. We're interested in convergence. So you might say you have a 19th order scheme, but it's interesting to see if it actually is. The preservation of correlations, which is what Peter was talking about earlier today. Horizontal and vertical coupling, because most dynamical cores are still horizontally and vertically split. So this means you do effectively 2D in horizontal, then 1D in the vertical, and this can have effects on accuracy. And finally, the one we look at is flow over orography. Now this becomes important when you have terrain following coordinates. I'll come to that later. So we saw most of this from Peter's talk. So we have the vector form of the tracer transport equation. But if you use the conservative form, then we need the density rho. Now our tests are designed so that rho should stay constant throughout the test, and therefore you actually only need to solve one equation if you're using the conservative form. Now the tests can be put straight into dynamical cores. What we do is we disable the dynamic updates of velocities and temperature, and we input this prescribed velocity that we give. And that's all there. So the first test is a 3D version of what Peter was presenting earlier. So we have the same equations that Peter used in 2D. We have this time reversing term, we have the solid body rotation. And what we do is we add this vertical velocity term. So the vertical velocity has got the sine of longitude, and if the time reversing term has a 2 pi t. So what this means is that one side will go down while the other side goes up. At the halfway point, they'll come back together. At 3/4, the other side will go down and go up, and then come back together at the very end. We have a shape function to make sure that the vertical velocity is 0 at both the ground and at the model top, so we don't lose our tracers. And because these velocities are non-divergent in the 2D case, when we add this vertical velocity, we have to add a horizontally divergent component to the velocity to make sure that the 3D velocity is non-divergent. Okay, so we effectively use the same thing that Peter talked about earlier. So we set up 4 tracers. We use a smooth tracer. So this is just a latitude-longitude plot at the middle height level. We use the correlated tracer, so we can look at the nonlinear correlations, and we actually use the exact same correlation that Peter used. These are the slotted ellipses, but the slot's actually in the vertical, so you can't see it there. And the final tracer we used is this multiple sum, and this again comes from the preserving correlations, because whereas most schemes can preserve a linear correlation, preserving a linear sum is more difficult, and we actually find that most of the schemes can't do that. So these are just plots at the halfway point. Again, it's latitude-longitude plot at a given height level. And here, this is comparing the CAMFV model and MCOR for the smooth tracer and the slotted ellipse. So CAMFV is well known, it's NCAR's model, it's finite volume on a latitude-longitude grid, and MCOR is what Paul was talking about earlier, so it's finite volume and it's on the cube sphere grid. So note that MCOR has actually been interpolated to the lat long grid for plotting purposes, so there might be a couple of interpolation errors, so I'm sorry, Paul. So the main things to notice is, first of all, MCOR is used without a monotonic limiter, which means we get these slight negative values and undershoots. But also, CAMFV is quite diffusive, and we can see that here, where it's diffused this tracer quite a bit more than MCOR has. So with this test, when we get to the final time, the tracers are returned to their initial position. So this is, I said, almost exactly the same as Peter's test. And this means that we can calculate error norms and other diagnostics. So the error norms we actually find that CAMFV performs better for the smoother tracer. And this might be because MCOR is producing a couple of overshoots and the negative values, whereas for the more steep-sided tracer, MCOR, even though it's got these undershoots here, actually has a better error norm. So the other diagnostics we looked at were the correlation plots, which again Peter talked about. So we have the two tracers, and we plot one tracer against the other, and they should follow this curved line. And as Peter said, when you go through the simulation, you'll find that they don't stay on the line. The mixing moves them back up. So they have these different criteria. There's the real mixing in here, there's the unmixing, and then there's overshooting. And so with DCMIP, we've got, here's just 5 models, just a brief into comparison. So we've got CAMFV here, we've got FV cubed, which is the GFDL version of CAMFV, but on the cube sphere. We have MCOR, and we can see the overshooting there. We have Endgame, which is a Met Office, and that again didn't use a monotonic filter. And finally have IFS. Now we can calculate the mixing diagnostics that are specified in the Ritson and Thuban paper, but I haven't done that yet because there's lots of data and it takes a bit of time to get through it all. So the second test is to investigate the horizontal and vertical coupling. So I said this is quite important because many models are still horizontally vertically split. So don't worry too much about this. The only thing to notice is we have the time reversing term again. And if we use different resolutions, we can calculate obviously convergence rates because we know the analytical solution at the end. So this shows the velocities v and w, and we have we'll initialize a tracer as a thin band sort of across here. We can see that this is going to generate some cells that will spin up the tracer. I've actually got a movie that hopefully will work. So it starts off as the thin tracer, and it gets pushed up, and at the end time it comes back together. So there's this bit here, which you can see as it gets stretched out. Our model here has diffused it, and it means that our final tracer's got these sort of gaps in it. So here's just comparing different resolutions. So this is 2 degree with 30 vertical levels, 1 degree with 60, and a half degree with 120. This is again for CAMFV, and this is at 2 times. This is at the half-time step, of the simulation. This is at the full time of the simulation. And as I was pointing out, you can see these bits get stretched out, and then when it returns, they're sort of missing here. And as we increase resolution, this gets better and better. So this allows us to calculate the convergence rate. And we find for CAMFV that the convergence rate for this test is for the L2 error norm is about 1.6, so it's less than second order, better than first order. But this test allows us to do this and see how well our schemes are doing the horizontal vertical coupling. So the final test to show is the flow over orography. Now this was discussed a bit yesterday morning, but we're using a slightly more extreme mountain. So the test is just a very simple horizontal solid body rotation. The mountain, as you can see, is quite an extreme form of the Shah mountain. We initialize tracers as thin cloud layers to try and make it realistic. And for models that use the terrain following coordinates, this test becomes quite difficult. So for for models with constant height levels, it's just 2D solid body rotation, there's no problem. If we use terrain following coordinates, as this hopefully shows, our model levels follow the shape of the mountain. Our tracer starts, let's just say, in these two model levels. It's just a vectored across, and we can see here that it's being forced into this model level, which it originally wasn't. We come here, it's now almost completely out of the model level it started in, and it's into these lower levels, and then once it gets past the mountain, it ends up in the levels we started with. So this is actually quite a challenging test for models that use terrain following coordinates. So these are the initial tracers, just to show, this is a longitude height plot along the equator, just to show that these ones are smooth and this one's not smooth. And I've got another animation for this one. Okay. So first of all, this is on model levels, and this is interpolated to constant height levels. So the reason the tracer seems to disappear is that it's a solid body rotation at a slight angle, and this is just along the equator. So it actually goes away, comes back, so it's over the equator at the mountain, and then effectively comes towards us and goes back to its original position. So we can see on model levels, we've got these wiggles as it goes over the mountain, and this is as it's being forced between different model levels. So even though there's no vertical velocity, there's no vertical velocity in the model levels, so it actually is transfer between the levels. So you see on constant height levels, what this does is it effectively makes it do lots of small vertical advection, and in the case of CAM-FV, this makes it very diffusive, and we start off with it at maximum at 1, and we end up with a maximum of about 0.3. So here's the plots again. So this is CAM-FV and this is MCOR. This is model levels at the top. So this is interesting because CAM-FV uses a hybrid pressure-based coordinate, and MCOR is the hybrid height. Is that right? Yeah. And we can see how at the halfway point over the mountains, the tracers have been merged into one. And with MCOR, it's doing slightly better. And we generally find that schemes that are diffusive will end up diffusing this out. Schemes that are not diffusive will end up producing lots of dispersion errors and waves across the domain. So this is what the tracers look like on constant height levels. So we can see here it's doing. We've got a bit of tracer then nothing, a bit of tracer nothing, and this goes back to here, where you can see in a model level you're going to have a part of the tracer, then nothing here, then part of the tracer. Yeah, so this is plotted on model level, and again we can see that MCOR seems to be holding the tracer together better than CAM-FV, and at the final time it looks pretty atrocious. We can calculate the error norms. I've only done this for CAM-FV in this half of the domain, and the error norm was of order 1. Which isn't good. So, as I said, we can put all these together. We can use all the results we got from DCMIP. So we had 18 models there. This is a snapshot of 12 of them. This is the test 1 that we showed at halfway through the simulation. And it allows us to look at all the models and compare how they're doing. We can see the CAM-FV and MCOR. We can see the negative values, the blue. CAM-SE, which is the spectral element NCAR model, which is going to replace CAM-FV, and that's doing very similar. NICAM's the Japanese model. We can see it's got a couple of negative values. Dynamical's French model, which hasn't got the negatives, but it seems a bit more diffusive in this area. You can see Endgame. Now, as I said, this hasn't got a monotonic filter, so it's produced these negative values. This is FIM, which is NOAA, and that's been quite diffusive compared to the other models.
What's the resolution on all of this?
So this is all 1 degree with 60 vertical levels, or equivalent. And yeah, it's worth pointing, models that aren't on native lat long grids have been interpolated to a lat long grid. So there might be a couple of interpolation errors. So if you're not happy with how your model's behaving, you can claim it's interpolation error. So FV cubed does similar to CAM-FV. We see that the icon model, Max Planck, is very similar to Endgame, to produce these negatives and then swirl them up. IFS is doing quite well, and this is Puma, which is again doing very similar. Yeah, so the point of the workshop is to bring all these models together. We can compare them like this. We can calculate error norms and mixing diagnostics. Now, we haven't done this for all of the models because we've got a lot of data and not had much time. And the aim of the project isn't to compare and see who's done the best, but really to help people see, yeah, well, first of all, you can use it for your model and assess how well you think you're doing, if you're doing as well as you thought you would, but also you can see where your problems lie. So you can see, for example, you might need a filter on here to stop the negative values, or you might realize that your model's being too diffusive here. So I've gone through that quite quickly. So the point of this talk was to present a set of test cases which hopefully we can use for 3D flow. They fit directly into the dynamical core. Just need to disable velocities and put our prescribed velocities in. The test should assess the things that we're really interested in with tracer transport, so physical things like positivity and the preservation of the nonlinear correlations, or the way our numerics works and the horizontal and vertical coupling. And then the final test was the flow over the mountain, which makes sense to test for terrain following models, but probably not for constant height models. And as I said, these tests were used at the DCMIP workshop, and we're hoping to, as time goes on, produce more and more results and get a better intercomparison. So I'll end up by saying thanks to all the participants of DCMIP 2012. So that's all the modelling groups, all the guest lecturers, and all the students. And if you're interested in DCMIP, Christiana's giving a talk later today, and we also have the website, which is there. So take a look, and thank you.
Thanks, James. Questions?
If you just clip the negative value, you will have the same pictures all agreed, which is that one.
Yeah, but then
In the presentation, if you just clip negative value, they all look the same.
yeah, this is
Just when you're showing the pictures.
This is just a quick example of a model intercomparison, or it was just showing that we can collect all the data. Yeah, we can look at anything we want. We can look at these plots, for example. It's just showing how we collect the data together. We're still analysing the data and looking at different things. They said they all look similar for that test, but at that point, but you can still see notable differences. So as you said, it's obviously the negative, but also you can see that some models are being more diffusive.
Yeah, I think difference in diffusion is important, but negative is not.
You can see sort of here and here compared with, say, there's CAM-FV. So there's, I know they all look similar for this test, but
So, given your preliminary look at the data, are there any lessons learned? I mean, can you tell us, is there any theme about what makes a good transport scheme or what makes a less good transport scheme?
I can give you a list of things that make a great transport scheme, but no one can do them all. So yeah, you could say you want things like monotonicity, but you also want high order convergence, and so we can. I guess the point of the DCMIP is to get the models and not, as I say, compare them to see who's best. But say if you bought your model, you could look at it and see maybe where your problems lie, or whether your model captures all the things you thought it would do.
But let's say I haven't built a transport scheme yet, and I'm going to build one, right? So I want lessons learned, right? That's
okay. I guess you could look at this, see which models are performing well, see what characteristics they have, and then build your model based on that.
A more specific version of that question. Was there any systematic differences between methods that did the vertical transport in operator split way and the ones that didn't?
I haven't actually had proper time to look at, especially for that test which had the horizontal and vertical splitting. So I don't know what the answer is. So sorry.
So related to that, is your boss going to give you time to do the analysis that you want to do?
I hope so, yeah. We'll find out at 5 o'clock today.
So the convergence result, was that for horizontal convergence or is it for both vertical and horizontal?
So it's for, so this is for both. So we've increased both horizontal and vertical resolution.
And so the convergence rate of 1.6 was for increasing both simultaneously.
Yeah.
One of the things Peter presented this morning was equivalent resolutions.
Yeah,
Is that something on your list?
it's something we could do. We didn't set out to do that, but there's all these different metrics we can use. And as we saw for the first test, we've used a lot of Peter's ideas already, so I'm sure he won't mind if we use a couple more.
Any more? Okay, thanks James again.